ago.
No.
All right, welcome everybody back to Math 131. I didn't label that. That's what this course is, did I? Math 131. We are now on Lecture 3. Today we're going to clean up. Go through our book and make sure we've covered everything. So have your book out for difference equations. We're going to clean up sections 1, 2, 10, 1, 10, 2, 10, 3, and 10, 4, and that's what you're responsible for in this course. Then we're going to slide on into the textbook where we will be the rest of the semester, summer session, sorry. And section 1.1 is just a quick algebra review of slopes of lines. You'd like to linger there for a while, but we only stay there a few minutes. But that's going to lead us into our introduction to derivatives, where our calculus class really begins, because derivatives can be defined as the slope of a curve at a point. And we've always talked about slopes of lines, but in life not everything is straight lines. So how do we find the slope of a curve at a point? And that will be our derivative. All right, well, I picked a fun problem for us to do that kind of covers a lot of topics, different concepts that we did in difference equations. And it's also a great little retirement problem, and it's a popular one that financial planners love to point out to people. And we're going to solve it using difference equations. Now, we're just going to keep 4 decimal places today because we don't want to type in so many numbers, but it's going to get an approximation, and it's okay because interest rates will never remain 8% compounded annually for the length of time that we're talking about in this problem. All right, so everybody will always want to have this problem on hand after you leave this class, because you will all be making financial decisions and paying my Social Security check, and I want you to have plenty of money to do that. All right, so what I figured was that for 15 years, we're going to deposit $3,000 at the end of each year in an account which earns 8% compounded annually. What we're really doing is I'm encouraging you, while you're young, to get what is called a Roth IRA. I'm not going to go into great detail what this is, except it's an IRA account that's purchased with money you've already paid taxes on, but now it grows interest-free until retirement, and when you pull it out, you still don't pay, not interest-free, tax-free. You never have to pay taxes on the money again, and you definitely want to do this while you're young. And so I would encourage you to check into a Roth IRA. So for 15 years, while you're working, making a lot of money, and for all the children need braces, college, cars, and all that stuff, you're going to deposit $3,000 at the end of each year in an account earning 8% compounded annually. All right, so then you're going to take a break. You're not going to make any more deposits for the next 25 years. You're just going to let the money sit there and continue to earn interest. The question then becomes, how much can you then withdraw at the end of each year for the next 25 years? These are your retirement years that you're saving up for. All right, I'm going to draw a picture. I'll put an age with it so you'll get a figure for it, a visual of what's going on here, and we know how to solve all this using difference equations. All right, first I'm just going to start out saying for 15 years, you're going to deposit $3,000 at the end of each year. So n is 1 with our difference equation. Remember, n is 1 period, and we're going to deposit $3,000. And you're going to do this for 15 years. Okay, so isn't that what the first part says? We make deposits at the end of every year for 15 years. N is in terms of years. All right, then we're not going to make any more deposits. No more deposits are going to be made for 25 more years. So in here we're going to have, I'll just do it like this, 25 years. And so when n is equal to 16, we're not going to make any deposits in there. Okay, and again, I'll come back with some ages so you'll get a feel for what I'm talking about. Okay, then you're not going to make any more deposits for 25 years. How much can you then withdraw at the end of each year for the next 25 years? So here's where that 25-year period stopped. Then we're going to pick up with the next 25 years. and at the end of each year, how much can you pull out, okay? And the account, we're just going to say, is going to earn 8% compounded annually for the entire time. Now, if you talk to a financial advisor, they would say that's a pitiful rate to expect over your lifetime. You should be able to earn over your lifetime a better interest rate than that. So we're fairly conservative here, okay? Fairly conservative. All right, so let's put some ages down just so that you get a feel for how I'm helping you out for your retirement years. I'm going to claim that you're going to start this at, say, age 25. I know that some of you are a lot younger than that right now. Some of you are a lot older than that right now, but you've started work and you're ready to save. All right, so if you are going to make deposits at the end of each year, so on your 25th birthday, you've made that decision, but you're not going to make that deposit till the end of your 25th year, which is really on your 26th birthday, right? You'd be better off if you'd go ahead and start on age 25, but we're not going to get into that because everything we've done in this course is ends of periods. That's called an ordinary annuity. There are other annuities where you put it at the beginning of periods. All right, so if we're going to do that for 15 years, I'm going to add 15 to 25. So you're going to make your last deposit 15 after that. That would be age 40. Is that correct? So at age 40, you make your very last deposit. That's 15 years. 15 years, 15 deposits. Age 40 would be about the time that you have to buy your children cars and buy them designer clothes and stuff. All right, then you're going to let the money just sit there in your Roth IRA, earning interest, but you're not going to make any more deposits for 25 years, so that will take you up to age 65 when you're about ready to retire. Although you guys really can't start getting Social Security till you're about 67 or 8. I don't know what it is. Okay? And so now you let it sit there for 25 years, and then at the end of each year for the next 25 years, so you let it sit there, so now you're going to come to the end of the next year and start pulling out your money, and that will take you up to the time you should die because you're going to run out of money, and that would be age 90. Okay, so you pull out your last withdrawal at age 90, and you go, okay, I'm going to be eating oatmeal or beans if I continue to live past age 90. Everybody see the story? Got it? All right, now I want you to take a second or two and just discuss this with your neighbor. We're going to be able to solve all this problem using difference equations. Think of the procedure you're going to have to go through because you've actually got 3 problems in one. Talk to your neighbor the game plan for this. You can only be talking about this math class.
I was talking about the book.
Okay. Talk about this problem. All right, I'd like to have a brave soul. Give me a game plan because there's really 3 parts to solving this problem. Where's the first part that you need to do?
Find the difference equation.
Okay, well, right, but for which part?
Yeah, the first.
Okay, so the first 15 years, we're going to have to find what? The balance after the last deposit? Okay, so the first 15 years, we're going to find the balance after the 15th deposit. Does that make sense? We'll know how much is in the account after the 15th deposit. All right? So that's the first thing we're going to do. So now we know how much. Let's get an overall game plan, then we'll break it up. Hold on. Okay, so we know how much we have at age 40. Now, what's the game plan for the next part?
Determine the interest and how much interest is.
Okay, so that's going to be kind of like just a compound interest, but it's a new difference equation because there are no payments. So now we have to find the next 25 years, and we're going to find the balance at age 65. And the difference is that we have to come up with a new difference equation because there are no deposits here. And so now we'll find out the balance at age 65. We'll know a present value or a y sub 0. We're just dividing it into 3 parts. All right, so now we'll know the balance at 65. And do you see now we have another whole difference equation where we're going to find the size of the payments or the deposits? Okay, so the third part is the last 25 years. We'll find the size of the annual withdrawals. Okay, do you see your 3 parts to your time diagram?
Yes.
All right, so let me just sort of divide them up and we'll do 1 part at a time. All right, so I need you to write the difference equation for the first problem, and then we'll stop and then we'll go to the solution. Write the difference equation for the first problem to find how much is in the account at age 40. What is y sub 0?
3,000.
0. The payments are equal. There's not, y sub 0 is always at the beginning of that little part of the time diagram, so y sub 0 is 0. So really, I didn't put any money in to get an account going. I'm just waiting until the end, and the 3,000 is what happens every year. Okay, so y sub 0 is 0. Okay, this should go pretty fast because we've been doing problems like this. We're writing a general formula for what's happening from one period to the next during this first 15. So y sub n plus 1 will be what? Y sub n plus the interest on y sub n. Y sub n times 0.08. And what's the time for that? 1, because it's year. It's annually. T is 1. And then what else goes in it? Plus 3,000, because there's your deposit. It's your y sub n, interest on y sub n, your deposit. Everybody got it? All right, so our difference equation then is 1.08 y sub n plus 3,000. All right. Of course, you're not going to want to generate one term after another, so you're going to go directly to the, what's it called? Solution to the difference equation. All right. Look up, everybody. They're looking down. Formula for solution.
E over 1 minus A plus y sub 0 minus B over 1 minus A raised to the negative.
A plus, A plus, A plus. All right, let's find this solution because we're going to be looking for what? Y sub what? Y sub 15. Because that's after 15 deposits. everybody agreeing with my work here?
Yes.
Okay, good. Thank you. I appreciate confirmation before I did the whole problem wrong. Okay, did you get something like 81,456.34?
That's right.
Okay, great. Thank you. Thank you. Thank you. All right, that we have made deposits of $3,000 at the end of every year for 15 years in an account earning 8% compounded annually, and this is what my account balance will be just after my last deposit. Everybody got it?
Yes.
All right, so we're right here on our time diagram. This is 8, 1, 4, 5, 6, 34. Right here. Now, my suggestion to you is that you start now with a new little time diagram, so you could call this your y sub 0. Do you see what I'm saying? So you don't have to keep going with numbers. So let this be your new y sub 0. And what are you going to be looking for? The difference equation, and we'll figure it out 25 years later. So now, go to the middle part of the time diagram, write your difference equation, and let's find the solution. Okay, this difference equation is going to be very easy. Remember, you're describing what's happening period after period, y sub n to y sub n plus 1. Okay, y sub n plus 1 will be equal to, let's put in all the steps. What is it?
0.
Y sub n plus the interest on y sub n, which n is 1 year, time is in terms of year, and then what's my
0.
plus 0? So this is going to be very easy. Y sub n plus 1 equals 1.08 y sub n. Okay, and do we know what y sub 0 is?
Yes.
Yeah, that's my 81,456.34. Everybody with me?
Mm-hmm.
Okay, so now where do I go to figure out y sub 25?
Your solution.
Yes, y sub 25. And I bet you love this one because b is 0, right? All right, I need somebody to double check me on this. Okay, I think I'm right. Did you get 557,851 about 72? Okay. All right, so you had $81,456.34 at age 40 if you started at age 25. Then you just let your money sit there and earn interest for you and keep your little hands off of it. And by the time you got to age 65, if it were at 8% annually, you'd be up to $557,851.72. I hardly know how to say these numbers, okay? All right, everybody good there? All right, that is the value right here, 557,851.72. right here. Are we good? All right, now let's look at the third part of the time diagram. So now we're only interested in this little part right here. We're age 65. We go to the bank and they say, well, you got $557,851.72 sitting here, and you say, okay, I'll be back at the end of the year and I'm going to start pulling out equal payments at equal time intervals for the next 25 years. And just after I've made the last deposit, what will my balance be at Y sub 25? Not deposit, withdrawal. Zero. Because you're going to use up your money. You're not leaving it to your kids to fight over. All right, so your question is going to be, find the size of the B. Exactly. Okay, set up your difference equation. Okay, help me with the difference equation. We're describing what's going on from one period to the next. So Y sub n plus 1 is Y sub n. What happens in between there? Interest. And then what happens? Minus B, because we don't know what we're pulling off. Okay, so Y sub n plus 1 equals 1.08 Y sub n minus B. And we know that Y sub 0 is 557,851.72. We know that Y sub 25, which puts you at age 90, is 0. And we're ready to go to the solution. So Y sub n is B over 1 minus A plus. Notice I didn't even ask you to tell me because I now have faith you know it. All right, so let's see if we can figure out things. We have A is 1.08. B is really a negative B, isn't it? In our general formula, A, Y sub n plus B. So my B is really negative. Okay, so quote B over 1 minus A will be negative B over 1 minus 1.08. Right, because it's a negative B. If that gets confusing any at all, I'll tell you how I normally do it in classes. Instead of calling it a B, I go minus, I just call them minus payments. And then you would know to put minus payment here so you're not saying B is minus B. Withdrawals, payments, whatever. Do you follow that?
You go ahead, I know the B part.
You like the B part? Since the general formula is A, Y sub n plus B, this whole little part right here is what goes in your B part of the formula. And that's really a minus payment or withdrawal deal. All right. The reason I want to be careful with those negative signs. So you basically are getting a negative over a negative, which is going to make that a positive. And if you want to go back to the B's, it'll be B over 0.08, right? So B times 1 divided by 0.08. So we're going to go 1 divided by 0.08 equals, right? B divided by 0.08 is the same thing as B times 1 over 0.08. Multiplication with fractions. And 1 divided by 0.08 is 12.5, so that's 12.5B. I lose anybody on arithmetic? You haven't done a fraction for a while? b divided by 0.08 is the same thing as b times 1 over 0.08. All right, here we go. So y sub n is 12.5b plus y sub 0, which is 557,851.72 minus 12.5b times a 1.08 raised to the n. All right, are we good so far? All right, now, I just used this little piece of information that we knew what y sub 0 was. We still have too many unknowns in here, but you know that after pulling it out 25 times, you're down to 0. So now we can use that. 0 equals 12.5b plus 557,851.72 minus 12.5b times 1.08 raised to the 25th. Okay? All right, it's like solving an algebraic equation now. We've got to solve for b. So just tell me how you would like to solve for b. There's various ways I could do it. Okay, let's do the exponent first and then distribute. That sounds like a good thing to do. And then we'll distribute. That way we can get all the terms with b on one side. Okay, so that's what we'll do. Okay, I'm going to put in all the steps so you can check me. .08 raised to the 25th is something like 6.8485. I'm just going to round to 4 places, 4 decimal places. That's going to make me off because we're going to be talking about $1 million here, probably. Well, no. But we have 2, 4, 6 significant figures there. 7, 8, 8. So I probably should keep a lot more decimal places, but we're just going to round. Okay. All right. So now I'm going to distribute this through, and I'm going to use my rounded to do it. Somebody sort of verify my numbers here. They are good. Okay, so I said 6.8485 times the 557,000 whatever and got 3,820,447.5044. Then I multiplied 6.8485 times a negative 12.5 and got negative 85.6063b. Got the b with it. Okay, good, thanks. All right, so the next thing we want to do is get all of our terms with b on one side, just solving a little algebra. Okay. All right, I think I'll take the b's over to the left. All right, so I'm going to say the 12.5, and I'm going to subtract from that 85.6063 and carry it over to the left, and that will be, can't even tell where my page is, 73.1063b equals 3,820,447.5044. Okay, so I said 12.5b minus the 85 gave me a negative 73, etc., with the b, added it to both sides. All right, and now I'm solving for B, so I'm going to divide both sides now by 73.1063. So we have 3820447.5044 divided by 73.1063. And you will be happy to know I ran this through a business calculator before I came. This is the correct answer. $52,258 and about 80 cents. What did we just find out? You're going to be able to withdraw at the end of every year for 25 years, $52,258.80. Let's look at what you put in.
40,000.
You put in 3,015 years, so you only put in, you're right. Yeah, 45,000. No, that's not right.
15 times 3 is 45.
Oh, yeah. I was doing 30. Sorry. Let's look at the amount of interest earned. All right. All right, let's look at my picture again because I just find this hard to believe. This is keeping your hands off the money, though. If you'll put in your money for 15 years, 3,000, let it sit there for 25. Then for the next 25 years, you can pull out $52,258.80 25 times. All right, let's see how much interest you earned. How do you determine interest earned? Common sense.
Figure out total.
Subtract 3,000.
Multiply that by 25 first, and then.
Okay, the difference between what you can pull out and what you actually put in, right? You can pull out this amount, $52,258.80. You can pull that out 25 times, assuming you live long enough. And what you put in was 3,000 15 times, 45,000. Correct. All right, so let's see how much interest we earned on this little account. This is called letting money work for you. Of course, it can't work if you keep pulling it out. Okay, so the amount of interest your account earned while you were there was 1261470. I don't see a decimal in there. Do you? That's it. That's how much how much interest was earned on your account over that period of time. The key to working these problems is keeping your hands off and starting early, because it's an exponential growth that looks like this. It goes very slowly. And then it starts to go like this, and you got to get way over here before you start making a lot of money. So start early saving, and then you'll be able to look after me.
Start early and put in a larger amount than 3,000. So I'd like to have that money before I'm 66.
You know what you should do is you should say, I want to retire at 55. So I know when I retire, I want to be able to pull out how much every year to live on. You work it back, and you could actually put in money every year till you retire, or you could really beef up the amount that you put in the beginning, or not wait till you're age 25, go talk to your rich relatives and ask them to hand you over some to put in savings. All right, you can have a great time figuring out these things. All right, don't you love difference equations? The answer is yes.
Yes.
Yes. All right. We are now going to clean up and talk through Chapter 10 and make sure we've covered everything in the book. All right, so I'm going to flip some pages, and we're going to work a couple problems as we flip pages that I looked at ahead of time. All right, so I've got our difference equation book open. I just wanted to point out a couple things. And I'm just going to do like speed reading. You'll remember that the first example is very similar to what we did the very first day. You put in some money. You just let it earn annual interest. We generated some terms. We found out what our Y's and 1s, 2s, and 3s, and 4s were. You may have to zoom in on that a little more. Yep. We learned how to generate some terms. Once we learned to generate some terms, we then started trying to figure out how you come up with a difference equation. And this was a difference equation that didn't have any equal payments or deposits. Okay, then the next thing they did in example 2 was they then started looking at, well, if you put money in, then you start making some little withdrawals. We didn't mess around with little pitiful $3 withdrawals. We made some nice withdrawals or some big deposits. And it shows you how you learn to set up your difference equation and then come up with it. Okay, so then when you flip over the next page, it said, well, hey, you could plot some points. We did that yesterday in yesterday's lecture, reminding you it's not a line, but it's a dot, 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 because n is 0, 1, 2, 3. It's not real numbers. And then in the middle of the page here is our solution to the difference equation that all of you have now memorized and learned how to solve. Okay, so the rest of section 1 was just simply that. There was not much to it, was there? All right, section 2 was trying to tell you also could do some simple interest. And I told you we would not be doing simple interest, but I'm on page 387 right here with example 3. What they wanted to do was then say sometimes your time is not just one, N represent 1 year, but it might be compounded monthly. So when you do monthly, they're using different symbols. I told you just to use the formula I equals PRT, and let me just show you that. They're using some different symbols here, which made it look harder, I thought. All it is your beginning balance, Y sub N, plus the interest on the beginning balance, Y sub N, 6%. Monthly, time is 1/12, and you get your Y sub N plus 0.005 Y sub N. When you say 0.06 divided by 12, so they're going to go into some symbols, R's over K's and all that, but it's no more than just using the simple interest formula, remembering that T is in terms of years. So if it's a quarter, what is T? 1/4, a quarter of a year, which is how many months? 3. Right, 3 months. So if you were making deposits every 3 months, your time will be 3/12. How about semi-annually? 1/2. Okay, so this section was basically trying to get you into when it's compounded more than just annually. All right, and that was pretty much that whole section. Okay, then yesterday we started looking at, well, how do you graph a difference equation without actually plotting points? And where I want to skip over to, I saw it earlier today, is on page 399, the various pictures here. Remember that we learned to say if it was monotonic, that means it's either increasing or decreasing. Increasing or decreasing. And how do you look at a difference equation? Not the solution, but you just look at y sub n plus 1 equals a y sub n plus b. What does the a tell you? What does a need to be for it to be monotonic? Positive. Because you remember in the solution it's the a that's raised to a power. So if a is negative, you know you're going to be bouncing back and forth, right? So you will have monotonic when a is bigger than 0. You will have oscillating when a is less than 0 because you're raising that a to a power in your brain. Okay, now we have the words attract and repel. Oh, by the way, what's the dotted line? The formula for the dotted line? B over 1 minus a. So we're either going to be attracted to that line or we're going to go away from it, which is called repelling. Now, we're still looking at A for knowing if we're going to be attracted to it. All right, so A is that number that's raised to a big power. So what's going to make it get smaller and smaller and smaller and smaller? Yes, when the absolute value of A is less than 1 because it's like raising a fraction to a high power. So when we have an attraction here, you got your y sub 0. If it's attracting, then we know the A is a number between -1 and 1. Can't be equal to 1 or 0. Okay, repel is when your A is going to be bigger than 1 because it's like raising 2 to a power. It just gets bigger and bigger. So it repels means it goes away from that line B over 1 minus A. Goes away from it. All right, so you just follow your little cookbook that I pointed out to you on page 398. Don't forget, one of the first things you always have to check is to see if y sub 0 is exactly equal to that B over 1 minus A. Because if it is, it's going to be a constant function. Yes?
If something's unbounded, is that the same thing as it being repelled?
Yes. Her question was excellent. The book talks about something being unbounded. That just means going away from the asymptote. It's just going to go on forever and ever and ever and ever.
But it doesn't mean it couldn't have another asymptote?
Right. It would not have another one, or we would have found it in B over 1 minus A.
Okay.
Yes. Unbounded just means it's going to go on forever this way or that way. Okay? Except I'm backwards on your graphs, aren't I? Sorry. All right. Thank you. Good question. All right. We'll use the words mono or oscillate, attract, or repel. And
It was in our homework as well.
Yeah,
it asks you for some unbounded questions.
Yeah.
But yeah, just unbounded, just think of repel. Yeah, it does. Okay? All right. Now, we have a fun problem that's similar to one of your WebAssign questions on page 402. Page 402, problem number 3. And you have a WebAssign question. The idea here is that we use graphing to make long-term decisions without having to go into solutions and getting exact values. When are things happening? Okay, and we're going to be able to use a graph here to help us decide. Question number 3. Upon retirement, a person deposits a certain amount of money into the bank at 6% compounded monthly, and they withdraw $100 at the end of each month. Okay, we're going to set up a difference equation, but the question is, how large must the initial deposit be so that the money will never run out? Okay, so you know, like when you when you start retiring, some people are scared to guess how long they're going to live. We guessed you were going to live to 90 a while ago, right? But some people want to go, okay, I want to make sure I have enough money so that if I live forever, you know, I'm never going to run out of money. All right, so we're going to have to figure out that, and we're going to be able to just use a graph to figure this out because we don't have enough information anyway to figure it out. All right, so let's draw a picture and see what's going on here. Let's see if I can draw it right here underneath. Okay, so this is number 3, and we're on page 402. Okay, upon retirement, a person deposits a certain amount of money. So we don't have a clue what y sub 0 is. Okay, we do know that it's earning 6% compounded monthly, and at the end of each month, n is 1 month. That means time is 1/12 in our little formula. They're going to pull out $100. All right, and it doesn't say how long or whatever. We just want to make sure we never run out of money. All right, so let's set up our difference equation. We'll go from y sub n to y sub n plus 1. 6%. Okay, so y sub n plus 1 is equal to y sub n. Y sub n times 0.06 times what? Everybody say it. 1 over 12. I can't tell you how often that gets missed on a test. Time is in terms of years. 1/12. And then we're going to pull off the $100. Perfect. So y sub n plus 1 equals, what's that, 1.005? Okay? All right, now let's make a little graph. And our guess is, what does y sub 0 need to be? Okay, let's get A as 1.005, B is negative 100, B over 1 minus A is negative 100 over 1 minus 1.005. 20,000. Thank you. Thank you. Is everybody good? Are you sure that's 20,000? All right. I would have thought it was 200. Okay. All right. So let's put in our dotted line. This is y equal to 20,000. Okay? Now the question is, what does y sub 0 need to be so that we never run out of money? All right, let's analyze it. A, which is 1.005, that is bigger than 0. So what does that tell me about my graph of this difference equation? Monotonic. So it's always increasing or always decreasing. Okay, the absolute value of A is bigger than 1. So it's going to repel the line y equal to 20. Correct? All right. So it's going to repel it. So if I pick a value less than 20,000 for y sub 0, it's going to be monotonic, meaning always increasing and decreasing, and it's going to repel that line. So what's going to happen? You're going to run out of money. Okay? If I pick a number bigger than 20,000 up here, it's going to be monotonic, and it's going to repel this line. Where is it going to go? Okay, you're going to leave a lot of money for your children to fight over. All right, so the question is, what is the minimum amount of money you need so you never run out? Exactly. If you do exactly 20,000, you would have a constant function, and you would never run out. So minimum 20,000, anything more is going to grow, actually. All right, is that good, everybody? That should be pretty much like your WebAssign question. Do you have it? Want to read it to me? We'll see.
I think I did something like that, but I got it wrong. Hold on. Let me find it. 1 second.
Okay.
Yeah, Fred wants to take out a loan. Suppose he can afford to make monthly payments of $600 and the bank charges interest at an annual rate of 10% compounded monthly. What's the maximum amount that Fred could afford to borrow if the loan is to be paid off eventually?
Eventually. Okay, so anything is going to eventually be paid off. The problem is he's going to be paying for the next 100 and some years probably, you know. So it is. It's just like this because you don't have a exact stopping date that you want it paid off. So if you came out with B over 1 minus A to be 20,000, he would have to borrow less than 20,000 to eventually pay it off. So you figure out your B over 1 minus A. If you borrowed that amount, recently people were getting mortgages, interest-only mortgages, which meant they were only paying the interest each month and never reducing their principal. They were being eat up in interest. Okay, but if you borrow a little bit less, you're eventually paying off your loan. Okay. So you would
has to be something less than the B minus 1 over
yeah,
A.
whatever B minus A is, it's got to be just a little bit less than that to eventually pay off your loan.
So if I type that in WebAssign, any number less than that, will it take it?
It probably is written to say, you just put in like 99 cents, come 1 cent under or something. I'll look at how the question is after class, but the wording should tell you how to put it in there so it's,
Oh, yeah.
what does it say?
In dollars, correct to the nearest dollar?
To the nearest dollar? Okay, then take $1
So I was
off
just-
of that. Okay? All right, everybody good? So you have a WebAssign question. What problem was that, by the way?
That was,
Homework.
it was difference equations 2, home problem 4.
Difference equation 2, homework 4, similar to this. All right.
On page 403, question number 27.
403, problem number what?
27.
27. A person makes a 6% compounded annually. Yep, it's just like number 27. Okay? How large must the money be so it will never run out? That will be exactly B over 1 minus A, right? Because then you're at constant. Is that good? All right. Okay, now let's look at 10.4. That's really what I worked you over from the very beginning anyway, because everybody loves playing with money. It started you out with an example 1 with a mortgage. We did that when we bought a car. Didn't we buy a car where we knew what we could make payments of yesterday, I think it was? And you want to know how much could you borrow? Same deal with a mortgage, monthly payments. Okay. We set up spreadsheets. They sort of have a little spreadsheet here in the middle of the page. Example 2 is finding the monthly payments. That was pretty much like the third part of our time diagram today when we figured out B. That would be the same way you figured out monthly payments. I'm trying to convince you I've covered this material thoroughly. All right. I think all that takes care of it. So you're good to go. All right. I'll ask you again Monday if you have some specific questions from the textbook that you could not get. Oh, by the way, nobody can ever find these answers. There's another divider in your book after page A4. Okay, it goes 410. Well, right before this little divider in your book is the answers to the odd problems. It's not all the way at the back. There's another divider. Do you see them? Okay, we're good to go? Everybody's happy? Great. Perfect. All right, we're ready now to start with the textbook. All right, so we begin in Chapter 1, Section 1. But before I begin there, if you are not good at negative exponents, and that seems to be a problem with a lot of students, you need to go to Chapter 0 in your textbook. Chapter 0 is an algebra review. And you will be crucified in this course if you cannot work with negative exponents. So you know that you want to do well in the class, and you can spend this Saturday night going through Chapter 0 reviewing. But I highly, highly recommend that you remember your quadratic formula and you work on fractional exponents, negative and positive. That's Section 5. And then Section 6 has the formulas for right circular cylinders, boxes. We're going to need those formulas once we start applying the derivatives in optimization. Work, work, work on negative exponents. You've got to be good. You just cannot survive if you can't deal with negative exponents. Okay? All right. We're starting in Chapter 1 because we assume that you're good in algebra. All right, and Chapter 1, Section 1 is just on slopes of lines and lines themselves. All right, so since this is considered review, I need somebody on the third row to already tell me what you know about lines or slopes of lines. Third row.
Vertical increase over horizontal.
Say it again.
Vertical increase over horizontal increase.
Okay, so you can have lines that increase or decrease. Is that basically what you're saying? So if it goes up like this is a line that increases, and this is an increasing line, and this is a decreasing. Okay.
I think he said.
Oh, vertical.
I'm defining the.
Oh,
The
that's a
change in Y
vertical.
or the change in X. Yeah. I think what he meant was.
And that's a
changing
horizontal. How does this relate to slopes?
I think he was saying the change in Y or the change in X.
Oh, change in Y over change in X?
Only he said it.
I'm sorry. I have a southern ear. Very southern. Slope is change in Y over change in X. If you have 2 points on your line, X1, Y1, X2, Y2, the change in Y is Y sub 2 minus Y sub 1 over X sub 2 minus X sub 1. Okay, so what kind of slope would this line have? Positive slope. positive slope. What kind of slope would this line have? Negative slope. What kind of slope would this line have? Zero slope. Because the change in y is 0 over change in x. What kind of slope does this vertical line have? No slope. Because you would have a number over 0, which is undefined. That's called a no slope. Okay, tell me what else you know about lines in second row. Anything. What else do you know about a line? Okay, y equals mx plus b. What form is that called? Slope intercept. Okay, which letter here represents the slope? That was a trick question. Slope. Okay, which intercept is this? Y-intercept. Y-intercept, where it crosses the y-axis. Okay, that's one form for a line. What's another form for a line? Is that the only one you know? Point slope, what's that? Y minus the y coordinate equals, right, and that just really came right here from this formula where you cross multiply. Okay, this is called point slope form, and actually this is the form I use a lot in this class because it's the lazy way. I mean efficient, not lazy, we're efficient. All right, equations of lines. All right, so let's just write an equation of a line, and then we'll look and see if what we covered. Write the equation of a line that passes through the point 2, -3, and has slope 7. Okay, write the equation line that passes through the point and has that slope. Okay. All right. You used point slope form. I would have used point slope form too. That seems to be the easiest. All right. Let's jump on the point slope form. Let me write it out. Y minus the y coordinate, because I see a mistake on your paper. Slope, unless I can't see it correctly. X minus the x coordinate. All right. So this is x1 and y1. Do you see your mistake? What have you got right here?
Y minus -3.
Oh, I didn't see that little minus up there. Okay, so you wrote it like y minus a -3? Oh, okay, I missed that little minus right there. Sorry. From where I was sitting. X minus 2, so you have y plus 3 equals 7 times x minus 2. That's a perfectly good equation for that line. If you want to go to slope-intercept form, that just means get y on the side by itself, correct? So we get y equals, what, 7x minus 14 minus 3? Y equals 7x minus 17. Okay, so same line. We're good. Everybody good? Equations of lines? All right. Section 1.1 also introduces you to some vocabulary that we're going to use once we get into derivatives. And it has, especially since this is kind of a business calculus, cost and marginal cost, revenue, marginal revenue, and profit and marginal profit. Okay? All right, so we're going to work on cost and marginal cost, and once we understand what that means, then we'll go right into revenue and profit. All right, and the example I'm decided to do is just one right out of the book and use it to help explain. So I'm on page 69. This is explained actually on page 61 in your book, but I'm going to do it from the example here. I'm on page 69 in your book. Marginal cost. It says, let C of x equal 12x plus 1100 denote the total cost in dollars of manufacturing X units of a certain commodity per day. So X is number of units, C is the cost, and this is going to be each day. And we're going to look for what is the total cost when we do 10 units per day, what is marginal cost, how do we use B and A to come up with C at 11. All right, everybody got your book looking at it? All right. So I'm going to move it over to the side. Here we go. All right, so we're on page 69, and I'm looking at problem number 47, and I just want you to reference you to page 61 where this is explained in lots of words. All right, we're given that the cost function, C of x, is 12x plus 1100. And we need to know what these things represent. C is cost, clearly. And x is number of units per day produced. Units per day. So if you were producing, making ties or shirts, how much does it cost you to make X shirts per day? Got it? If you were graphing this, along this axis you would have X, and I believe X would have to be numbers 0, 1, 2, 3, because you wouldn't be making part of a shirt to get the cost maybe. I would probably do dots, but anyway, when X is equal to 0, we would start at 1100. Somebody translate for me what C at 0 equal 1100 means. Right. Before you ever make that first shirt, it's going to cost you $1,100. That's called a fixed cost. That's for your building, your equipment, insurance, rent, whatever. That's your fixed cost. It just costs you that much to even get started. Then this has a slope of 12. So the next little place you know would be, what, 1, and you're going to go up 12 on that. So that would be, what, 1, 1, 1, 2. Because your y value went up 12, slope up 12 over 1, up 12 over 1. All right, so it means that the variable cost, here's your variable cost, it's going to cost you $12 per item once you start at your initial cost of $11.10 to get started, $1,100 to get started. Is that clear, everybody? Okay, all right, so cost is what it actually costs you to make your product. All right, Part A. Part A says, what is the total cost if the production is set at 10 units per day? That's a slow business. Maybe they're only going to work 15 minutes. All right, so you're only going to make 10 units. So how do you find the cost when you produce 10 units in a day? Yeah, C at 10. So you have 12 times 10 plus 1100. And I guess that would be 120. Oh, I should be able to do that in my head, right? 1220. Is that right? Okay, so to produce 10 units, that just means you have a dot sitting out here somewhere of 10, 1220. Okay? All right, B. This is our new word, marginal cost. What is the marginal cost? Okay, for all you people who've had economics, impress me. What would it mean for marginal cost? Yes, That is so well said. Say it again.
How much it takes to build one more unit?
Well, what is the cost, to manufacture or produce one more unit? Wherever you happen to be, what is it going to cost you to do one more? Exactly. Perfect. All right, so no matter where I am, this happens to be on a straight line. So no matter where I am on the line, what's it going to cost me to do one more? What is it going to cost me to do one more shirt? $12, my slope, right? My slope here is 12, so wherever I am, whatever I've produced, to do one more, it's going to cost me $12, correct? Okay, so the marginal cost here is $12. Wherever I am, to produce the next unit will cost me another $12. All right? Now, the next part it's trying to bring to you is it says use part B to come up with the cost of 11 units. All right, well, we know if we just want to do the cost of 11, we just put 11 in here with the 12 and then add it to this, right? Okay, but if you think about it, you're already at 1,220. What is going to be the cost to do 11 units if you know you're going to do one more? Yep, you're just going to take the cost at 10. Let me write it this way. Cost at 10 and add your marginal cost, right? Because you went up 12 over 1, up 12 over 1. So the marginal cost is the slope of that line. All right, so that would be 1220 plus 12 is 1232. Is that right? Okay. All right, so repeat the definition of marginal cost for me again because you did it so well. To build one more unit. Perfect. Wherever you are to do one more, that's going to be your slope in there. This becomes very important in the next section when we start talking about derivatives. All right, somebody define for me what revenue is when you're running a business. It's not how much money you make. What might that word be? Profit. Profit's what you really make. What's revenue? How much money comes in? How much money is in your cash register at the end of the day? Because the amount of money that you bring in doesn't mean that's how much you really made. That's how much you brought in, right? So revenue is how much money you bring in from the sale. All right, then what is profit related to those words? Yeah, profit is revenue minus cost. And if your revenue is less than your cost, you're in bad shape, right? You wouldn't want that to happen too long. All right, now that we got that, I need somebody else, although you did such a good job with marginal cost. I don't want you to answer this one. Somebody to tell me what the marginal revenue in words is. Marginal revenue. Tell your neighbor, and then you can pick somebody to tell me. Tell your neighbor what marginal revenue is.
Enough to sustain
revenue.
enough.
Not make.
Enough to pay the marginal cost.
Money comes in when you sell one.
Okay. What'd you say?
I said enough, and the least amount of revenue you need to pay for the marginal cost. I guess something like that. No, I didn't say that, but I can't remember.
That's what she said, right?
Yeah, that's what she
All right.
Yes, I forgot.
What did you say?
Enough money to sustain a business.
No, I just want to know what marginal revenue is. Say it again.
The money that comes in when you sell one unit?
One more unit, right? It's the extra money that comes in that day from the sale of one more unit. So in general words, what would that be? The selling price of your shirt, right? Right? The marginal revenue. You're selling your shirts for $20. So if you sold one more shirt that day, your extra revenue coming in would be $20, right? Okay, let's try again. Marginal profit. Tell your neighbor what marginal profit is.
How much do we call it? One more unit.
Okay. All right. You want to try it?
No.
Okay, so whatever you sold that day and taken into account the cost, it would be the extra profit you actually come away with from the sale and the production of one more item. Okay, one more. Marginal, one more, wherever you are. Everybody good? Okay. You're going to use this a lot in this course. Make sure you're good with cost, revenue, and profit. A lot of people, when they say revenue, they go, what you make. That's not correct. It's how much money is in your cash register at the end of the day. Okay? All right, let's look at problem number 49. I thought this one was pretty good since we just got an announcement the gas prices are going up again this weekend. Did y'all hear that too? I heard it's, I hate to say it because by the time people are watching these tapes 3 or 4 years down the road, they'll go, that's cheap. Why are you doing that? It's supposed to be over $3 after the weekend for regular. Yeah. Yeah, I know. All right. Problem number 49. The price of 1 gallon of unleaded gasoline, this tells you how old these problems are, at the pump reached the all-time high of $1.69 on January 1st. And at one time we just went, that kills me. And now we go, if we can just find it, $2.50 a gallon, that'd be great. Okay, but now it's about to go to 3. All right, but this was on January 1st, 2004. And it continued to rise at a rate of 6 cents per month for the next 9 months. Okay, so what we want to do is come up with a formula that expresses the price of 1 gallon of unleaded gasoline as a function of time for the period starting the first day of January 2004. All right, so we're going to we just want a formula that will describe the price of the gas. X would be what? Your number of months after January 2004. All right, so the gas on January 1st, 2004 is $1.69. It's going to go up 6 cents a month, where X represents your number of months. Write your formula that's going to describe the cost of gas, or your price for gas. Oops. All right, so the price based on the number of months after January 2004, what's my formula going to be? 1.69 plus 0.06 times X. So when I ask you what is P of 0, I would get 1.69. So when X is equal to 0, that corresponds to January 2004, correct? All right, so we need to get our bearings. That's why I did this, so we can answer the rest of the question. Everybody good so far? All right, first question is, so what was the price of 15 gallons of gasoline on April 1st, 2004? All right, so January is 0, February is 1, March is 2, April is 3, correct? Yeah, the reason I did this was because I thought you'd say April 4th month, X is 4. But you had to start with January as being your initial 0. So April then will correspond to 3. So P of 3 is 1.69 plus 0.06 times 3. I know y'all want me to do this in my head, but I'm really needing a candy bar. Sneakers or Baby Ruth would be great. 187? That's exactly what I thought it was going to be. 187. All right, well, I thought this problem was a bit outdated for us, so why don't we figure out what it would be if we continued this on till today. All right, so this happens to be July 2006. All right, so January 2004 to January 2005, that would be a x equal to 12, correct? 12 months later. So January 2006 would be 24, correct? 24, and then we have, count on our fingers, plus 6. Is that? But you go a whole year to get to your 12, right? So let's double check that. I like to count on my fingers. So January is 24. January, February, March, April, May, June, July. So 24, 25, 26, 27, 28, 29, 30. Aren't we thankful for fingers? Exactly, 30. All right, so let's figure out P of 30 and just see if we're anywhere close to what the gas prices are today. Don't you just love math? Aren't you having a great time? Anyway, you'll be happy to know I don't let you leave till you tell me you are. Okay. So now, when you complain that the gas prices are around $3 a gallon, although when I went up to D.C. recently, I saw some gas prices along here, $3.49. All right, so if it'd gone up 6 cents every month since January 2004, we'd be at $3.49 a gallon, which we're probably not really too far off, especially if it wasn't the regular. All right, everybody good? Happy? Okay, I want to give you some insight where we're going to start next time, and if you hear a little bit today, it makes it easier next time. All right, section 1.2, we have slopes of a curve at a point. All right, so far, all you've ever worked with are straight lines. And you know the slope is the change in y's over the change in x's. Now, we know that life is not all about straight lines, but about curves. How are we going to find the slope of a curve? Slope of a curve. Slope of the curve. Yes, at a point. All right, so what we're going to do is we're going to come in on our line, on our curve, and we're just going to blow it up really, really big. So this little part now becomes this big old dot. And we have this little part going through that little dot. And what we're going to do is come in with a line that best fits the curve at that point. We're going to look for a line that best fits the curve at that point. It's the line that best fits. And we will get the slope of that line. And you've already told us what that line is called. It is called the tangent line to the curve. So the line that best describes it. And then you just extend it. And if we get the slope of the tangent line, then that will give us the slope of the curve. Okay? So what you will want to start processing in your brain are 3 things that mean the very same thing. 3 things meaning the same. slope of the curve at a point, slope of a tangent line to a curve at a point. And the third thing, which is what calculus is all about, derivative. The derivative is the slope of the curve at a point. It is the slope of the tangent line to the curve at a point. Derivative. All those are the same little bits and pieces. Okay, let's just do a real easy problem and then we're going to take a break until next time. Suppose that my function is y equals 3x plus 1, which is a line that looks like this. Y-intercept here is at 1. If I ask you, what is the derivative? What is the derivative of this function at this little point right here, whatever it happens to be? What would be the derivative of y equals 3x plus 1? The slope, which is what? 3. If you have a straight line and the tangent line are the very same line, because if I'm at this point, the line that best fits this would be the line itself. And the slope of the tangent line and the line are the same, so therefore the slope of the tangent line is 3, meaning the derivative is also 3. All right, so the derivative here is 3. All right, suppose my line looks like this is the x-axis and this is the y. Suppose I have a horizontal line such as y equal to 4. What is the derivative of y equal to 4? 0. That is a slope of 0. Okay, how do I get a derivative that does not exist? All right, if I have a vertical line, let me write this. Derivative equals 0. Okay, if I have a vertical line, like, what would be a good equation for this line? X equals 2 or something like that, x equals 2. This is a line with a no slope. If I ask you what is the derivative, does not exist. Derivative does not exist because there is no slope to that line. Okay? All right, I want everybody to look up. Don't look at my paper. When I say the word derivative, what is one thing that's going to pop in your brain? Slope of the tangent line to the curve at a point, or slope of the curve at a point. All right, turn to your neighbor, tell them those two things. What is the derivative? Don't read it off.
Slope of the curve and the slope at a point. Slope of the curve at a point.
All righty, I'm going to go around and point. You say it right, and we're done for today. All right, if I say derivative, what are you thinking of? Don't look.
The slope of the tangent
Line.
and of the curve. Of a point. At
The curve.
At a point.
Okay, so try again from the start. Quickly, so we can get out of here. Say it again.
The slope of a tangent line of a curve at a point.
Perfect. All right, tell me something else.
Slope is the derivative. Does that count?
No, I want to know something else for the derivative.
Slope is the point of the curve. The derivative is the point of.
The derivative is the point on the curve. What do y'all say?
No.
No.
It's the slope of the curve at a point.
Slope of the curve at a point, right?
Point.
Slope of a curve at a point is a derivative. Everybody got it?
Yeah.
You'll know it Monday when you get back. Have a great weekend.